Hello everyone, welcome to this video. In this video, we shall be learning about a criteria which is used to determine that when can we say any direct product as cyclic, right? So let's have a look here onto this result. The result here tells us that if G and H are two finite cyclic subgroups, right, that is given to us, they are finite and they are cyclic, then their direct product, G direct product with H, that would be cyclic if and only if their individual orders, that means the order of G and the order of H, they are relatively prime to each other, right? So this is the result. So here we have to prove the result in both ways. First of all, we will assume that G and H are any two finite cyclic group. That is obvious, right? Next, we will assume first of all that this direct product is cyclic, and we will prove that the orders G and H, they are relatively prime to each other, and conversely we will assume that these orders, they are relatively prime to each other, and we will prove that this direct product is cyclic, right? So here we assume that the order of the group G is M and the order of group H is N. Then what would be the order of the direct product? You know, in direct product G direct product with H, we have elements of this kind where we have tuples, right, where the first element has been taken from the first group and the second element is taken from the second group, right? So if there are M elements present in the first group, so that means there are M choices in order to select this G, right? And if there are N elements present in the group H, so that means there are N choices in order to select this. So in total, the number of such pairs G comma H would be M into N, right? This is according to the general Cartesian product of different sets, as you know. So here we have the order of G direct product with H as Mn. Now we are first of all assuming that this direct product is cyclic, and we will prove that their orders are relatively prime to each other. So we will prove that the GCD of M with N is equal to 1. Why? Because we wanted to prove M and N are relatively prime to each other. So we first of all assume that this GCD is equal to D, and we will then prove that D is equal to 1. So we assume that this GCD is equal to D, right? Now because G direct product with H, that is cyclic, so therefore there must be some generator of this group. Let's call that generator, because all the elements of this group direct product, they are of this form, G comma H form. Therefore we are assuming G comma H to be the generator of this particular group. If this is the generator, then moreover we know the order of this group is M by N. So that means any element that is raised to the power Mn, right, that would be identity. Yes, EE, because Mn is the order here. So let us now, because we wanted to prove D is equal to 1, we consider G comma H raised to power Mn by D. So we can take this power Mn inside, so it would be G raised to power Mn by D, comma H raised to power Mn by D, right? So now you can write this as G raised to power M raised to power N by D, and you know M is the order of the group G and small g is taken from the group capital G. So that means this element would have, G would have the order M. Why? Because here the order of element is equal to the order of the group, because we are talking about cyclic groups. So therefore this thing would become e to the power N by D. And similarly here for the second term, what we can do, we may write this to be H raised to power N and then M by D. And you know the order of this group H is small n, right? So what would be the order of some element which is taken from here? It would also be N, because the order of element is equal to the order of the group in case of cyclic group. So this thing becomes the identity. So we would have e to the power M by D, and you know identity to the power anything is identity, and identity to the power anything is identity. So that is how we have this identities over here. So that means from here we obtain that, because we know that the order of G direct product with H is equal to Mn. So therefore its order would also be Mn. Why? Because we are considering this set group of direct product as cyclic. So therefore its order would have the same, its element would have the same order, right? And from here we have obtained that when we raise this element to this power Mn by D, we would obtain identity. So that means this Mn by D is obviously greater than or equal to the degree of this element G comma H, right? So that is what we are saying over here. So from here we obtain this Mn less than equal to Mn by D. And when is this possible? This is only possible when D is equal to 1. And exactly we have the equality here. So from here we obtain D is equal to 1. And this is what we wanted to prove here in the first part. For the second part, we assume that M and N, they are relatively prime to each other, and now we will prove that this direct product is cyclic in nature. So here we are assuming that we have cyclic groups G, which is generated by the element small g, and the group capital H, which is generated by the element small h, right? This group G has order M, this group H has order N, and both M and N, they are relatively prime to each other, right? This is our assumption. So that means the GCD of M with N is equal to 1. So in order to prove that G direct product with H is cyclic, what we need to prove? We need to prove that the order of the element, some element GH, that is equal to the order of the group, right? If that is so, then this element would become the generator of this element. So here let's take the order of the element G comma H. Now from the previous result that we have studied, the order of the group G plus H, that is equal to the order of some element G comma H is equal to the LCM of the individual groups, right? This result we have already studied. So therefore the order of G comma H is equal to the LCM of the order of G and the order of H, and the order of G is M, the order of H is N, right? So therefore what is the LCM of M and N? When both of them are relatively prime, it is just Mn. And what is Mn? Mn is the order of G, the direct product of G with H. So therefore this order is equal to this order. So that means this element G comma H becomes the generator of this group of direct product. And if this becomes the generator here, so that means this group is cyclic in nature, and this is what we wanted to prove here. And in fact, for this result, we may generalize this result. This result is defined for two groups which are finite cyclic groups. Then we are saying this direct product is cyclic if and only if their orders are relatively prime. Now we can generalize this result over here up to n groups. Suppose we have G1, G2 up to Gn group. Now what is the criteria for them to be cyclic? Their direct product to be cyclic. So we will say their direct product would be cyclic if we consider all of them to be finite cyclic groups whenever the order of each of the group that is relatively prime to each other. So that means if we take different groups, their order should be relatively prime to each other. If that is so, then this external direct product is cyclic and vice versa. So I hope you understood this result well. Well, that is it for this video. Thank you for watching.